Well, I did fill in the middle that was missing. I think slide 8 to the end of adulteration. Hopefully that's all you're missing out of that. And of course, I couldn't help myself but go through the notes again and add some things to them and delete some things. So anyway, there's another set of notes that I sent to you this afternoon. If you want, download them, or you just find some things inserted. How's that? Some things missing. We do have the final next Tuesday night. It's only be an hour exam. It'll be on the last half of the class. So from the time of the last exam up through the end of the semester.
You had covered one lecture on both sides, so that material also be on exam.
One lecture on both sides of?
Yeah, it was on encapsulation methods after silicon, or including it after.
Oh, so I quit in the middle of a presentation. Did I ask questions on that?
On the first half of the presentation.
In the first test? If I had to ask some question about encapsulation, no, then that's fine. It'll just start after encapsulation. Yeah. Any questions before we get going? There is a lab tonight, but he's been working on some emulsions and some other things. So anyway, that'll be kind of the usual. So if nothing, away we go. I think I left with this slide, or maybe it's the one after this. And I don't know, I hope you see what's the meaning of this or understand what this means. And so I just want to take another moment for that. Flavors are a mixture of compounds. Obviously, they're quite a complex mixture of compounds commonly. And if we're talking about fat and the role it has on changing flavor, changing intensity of flavor, changing character of flavor, and this slide illustrates why that tends to happen quite well. Because over here we've got 0% oil in the model system, and there will be a certain vapor pressure, a certain flavor intensity that comes out of this. And so if our flavor mixture of these four chemicals, okay, this would be our blend with no fat, at least from a perception standpoint. And as we add fat, the butteriness, we can go down a great deal as we start adding fat to that food, to its basis. But something like this ester, 10% drops in here, 1% fat drops it way to here. So at 0% fat, you'll find you've got a lot of this ethyl fruity note, but to make it 1%, that fruity note is really diminished. Over here, propanol isn't a flavor compound, but it's just a water-soluble compound. It could mimic a flavor compound, but it's almost unequal. So some parts of your flavor really go into fat and they disappear. Those components are lost, and other ones, stay at their normal level. So really, adding fat to a system or changing the fat level in a food has a major effect upon what you taste, both in terms of intensity and in terms of character. And so that's basically what it says here. Water-soluble flavors not really influence much, but any fat-soluble flavorings have to be increased substantially if you start putting fat into that food. So this one I'm always interested in, and I'm never quite happy with it because what this is trying to show is what happens if you simply put flavor and water together, or you go ahead and make an emulsion out of that flavor and water. Would emulsion have more flavor or less flavor than simply mixing the system together? And this is diacetyl, so it's like water-soluble flavor. It's a little interesting why we even do this, but they're adding ground nut oil to it. And so diacetyl, water-loving compound, in a water system. And so you look at the vapor pressure volatility. If it's making emulsion, it kind of goes up with our concentration. On emulsified, really isn't much difference because some people say, gosh, if I make an emulsion, will it change my intensity of flavor? For some compounds, especially water-soluble compounds, it doesn't. A lot of interest in nanoemulsions. And they want an adding emulsion sometimes because they feel it's going to give them a burst of flavor. But I don't see that. And to me, it just needs a little more work to say, what is the situation in this case? But that one says it doesn't matter if it's an emulsion or not. It's totally based on the amount of oil and the amount of water you got in that system. That's what determines its intensity, what you perceive. Just that balance of oil and water. It doesn't matter if it's emulsion or if it's a 2-layer sitting there in a beaker.
Well, would this change if it was overshot by it?
It shouldn't. No, this is an equilibrium. Once that equilibrium is established, it won't change. Compensation for changes in fat levels. Well, I think I've mentioned this. We can understand this. We can predict it. It's just fairly simple physical chemistry. So we can look at solubility limits, what we know about flavor molecules and fat, what we know about water. We've really got enough information that you can adjust your flavor level and be able to predict how that's going to modify your perception. So mathematical modeling, it's pretty straightforward stuff. And so we really could adjust our flavor. We could look at the flavor compounds that are in there. We could look at their water-soluble fat solubility and look at a product and say, this much fat, how much water? We need to add this much more of that compound or less of that compound. So we can do the math and we can take care of it. But the problem is that oftentimes we don't have that control. We're maybe using natural extracts, natural flavor blends. And we can't tell nature that we want it to change because I'm adding fat to this product or taking fat out of this product. Like chocolate, for example. Chocolate, not an awful lot of fat in chocolate. And what we perceive as chocolate is how these 900,000 different aroma chemicals in chocolate, how they partition between the fat in the chocolate and the water-soluble part of the chocolate. And so we can't really change the chocolate to compensate for more fat or less, because we don't have control over each of those chemicals in chocolate. So if it's a synthetic flavor, I know every chemical, I know the concentrations, I can fix it. If it's a natural product, it's a natural blend, I don't have the freedom to change that blend.
Yeah. So you're saying just like a natural, like by regulatory standards, natural flavor is harder to compensate for? Because you can have natural.
If you have natural pure chemicals, then
you're saying
okay.
like intrinsic.
But yes, right. Like an orange essential oil, a lemon oil, an essential oil, or a chocolate, or a meat flavor, or any of these things that they are the actual caramelization. We can't change that flavor. We can't change the chemistry that happens in that flavor to make it adjusted for changing fat content. And it's interesting too that there was I don't know what he was, a neurologist or something along those lines that was looking at fat receptors. And you probably have all heard of fat receptors. So do we have a fat receptor on the tongue? Do we have one someplace in our gut? Do we monitor calories or something that's coming along that comes from fat? It's interesting. We learned to associate between food and calories. And so basically some of the theories is that your body expects a certain number of calories associated with a certain flavor, a certain texture. And if that isn't right, I don't care what you do. It isn't going to be judged as right. That's a fascinating one too. And again, in that case, if there's an association we expect between calories, for example, and a food product or flavoring, how do we fool the brain to think, no, you got to be happy with this. This is really good, even though it doesn't have calories. And so it's one of those things that just really isn't that simple to manage. And I think every time we think we've learned something, we find out we don't know it. There's another thing we need to learn, unfortunately. Well, that's fat. Like I say, fat's reasonably manageable in comparison to the next two that we go through. And so another food constituent that's important to me, of course, are carbohydrates. And so what about carbohydrate flavor interactions? We divide them into two different categories of reactions. It can have a chemical reaction, which is a very direct effect. So maybe a carbohydrate binds some flavor chemicals, takes them out of the system, reduces them from perception. So that's a chemical interaction, very direct effect. And then there are also a physical effect. Do carbohydrates form a physical barrier to the release of aroma chemicals, so they're released from the food to smell or perceive? And they're very, very different between each other. So this would be a very specific effect. Some chemical really likes some carbohydrate component, it's going to bind, we're going to miss that part of the flavor. This is physical, and it keeps any chemicals from going out, being released from the food for perception. The direct effects can be put in any of these categories. Hydrogen bonding, ionic bonding, hydrophobic bonding. Covalent is less available for us in carbohydrates. We don't find a lot of sugars have the right structures to react with flavor molecules. And what I've added to the presentation is really now about proteins. And so if you've heard me talk on protein flavor interactions, you're going to hear a little more about it. And so for proteins, we're really interested in covalent bonds between a protein and a flavor molecule. I say it's less important for carbohydrates. We don't find the same reactivity. And again, all of these interactions are dependent upon the structures of the sugar and the flavor molecules, so they can be very specific. Part of your flavor can be targeted, be reduced. Other parts may be unchanged by the carbohydrate present. And when we think about the indirect, the physical barriers, we've oftentimes looked at things like viscosity, and same with gels. For a long time, actually until 1995, that's quite a long time, so 35 years or so, a lot of stock was put in the idea of gel structures, viscosity, are very, very influential on how we perceive flavor. And as we'll probably see, we're going to come to that in greater detail. So maybe let's wait with that one and explain the idea of viscosity and gel on carbohydrate flavor interactions, and go on and come back, like I say. Simple sugars, so we'll kind of look at carbohydrate interactions with simple sugars and work our way up to more complicated carbohydrate systems, whether it's be starch, gums, and those kinds of things. And for simple sugars and high potency sweeteners, a small amount of sugar, 5-10%, really tends to balance a flavor. Balance, round it out, and it's very, very desirable. It makes the flavor more natural. It makes the flavor come out of the product or be perceived more strongly. And so some sugar, when it's expected, is good. If you look at bulk sweeteners, people have talked about this a great deal. Bulk sweeteners, I'm talking about sucrose, fructose, cornstarch, some of these kinds of things. They can certainly have an effect upon flavor materials that are released in season. They may solubilize flavors, make them more soluble when they stay in solution. So that's an indirect effect, making them a better solvent. Sugar water is maybe a better solvent. And one that we oftentimes hear about is solving out. And perhaps what solving out is, in the sense that if you add salt to a solution, it's going to tie up some water. If there's less free water, there's not as much solvent for the flavor, so the flavor tends to give up. And that's what I've never liked. It takes about 40% salt, which is beyond its saturation point, to actually have an effect, a physical effect of binding water. So I really don't like that idea. And what we're going to talk about a little bit more is that sugars do have an effect on flavor perception. But it's more a matter that the sugars change the water. They change the solution. They either make it more suitable or less suitable for the flavor molecule to stay. And so this effect is not uniform. It really depends upon what flavor compound we're talking about. And of course, it depends on monosaccharide, disaccharide. Monosaccharides, remember, there's many more of them per unit weight. They have a greater impact on solution than do disaccharides. High potency sweeteners, you'll wonder, okay, what do they do? I don't know how many of you like a diet beverage versus a sugar sweetened beverage. I probably mentioned I like diet beverages. You give me a sugar sweetened beverage, it feels viscous in my mouth, and it's sickeningly sweet. It's not. I just don't care for it. I like dietetic beverages, and so it's interesting. Of course, when Coca-Cola, Pepsi, all these companies change their products from full sugar to diet, there's a change in flavor, and that everybody recognizes. Diet Coke does not taste like sugar sweetened Coke, even though they put the same flavor system in there. It's not the same product. Why? It can be different factors that enter into it. It can be physical chemical effects. So maybe those sugars are having an influence on the solubility of some flavor molecules in a flavor mixture. Maybe they're making it better solvent, so they're kind of depressed. Those that aren't influenced by the sugar changing the solution, they're more enhanced, or at least not bothered. So we have physical and chemical effects in the beverage that changes the balance that we're given for reception. And some people talk about receptor effects. Is there still receptors for sugar? Most of the time, high potency sweeteners only stimulate one of those receptors. And so your brain is going to know something's wrong here. Sugar, it's sweet. Yep, they're both sweet, but that's not right. Sugar is sweet. I associate with both receptors being responsive, and if they're not, it creates some issues, more perceptual effects, and how we process this, or the expectations, so on. That's an interesting one. Catherine Diebler presented some work that okay. How do we put that? I don't believe. That's one way to put it. This was at a conference in Increase where she put individual flavor molecules into an aqueous solution, then added aspartame at some isosweet level, sucralose isosweet, so they're all the same, adjusted the same sweetness, and then looked at the head-switch, the volatility of each of these flavor compounds. And so it was interesting to me that she found the difference between aspartame, sucralose, and acetate. So isoamyl acetate, no effect. Aspartame added, aspartame solution, or acetate, acetate. But sucralose, due to drying these out of solution, you get a higher vapor pressure, higher volatility, greater perception than you anticipate. And so there's this combination of results where sucralose seems to have a greater effect on these aroma chemicals and how they would be released and perceived. And what troubles me so much is that aspartame is probably 100 parts per million, 150 parts per million. I can see no possible way that 100 parts per million of some non-reactive chemical is going to make something more volatile or less volatile. You got to get to 5%, 10%, 20% of a material before you see an effect of it on volatility, forcing out greater solvent. So I kind of looked at that and I kind of let it go, but I just don't. I have problems along these lines in terms of thinking that flavor is changed because of increasing. And how do you increase it? I could see if a flavor molecule chemically reacted with a high potency sweetener, it could decrease it. But how on earth do you increase it?
The mild beverage is all not sugar, or was it a sugar-free?
That was a sugar-free. Yeah. So the only thing is, 100 parts per million or less in some cases. I don't remember what sucralose was. And so the idea of simply forcing it out of solution, making it more volatile or chemical, I can't deal with. That's another way to put it. And what some companies do, though, is they look at blends of high potency sweeteners, and that's what we see a lot of today. Not depending upon a single sweetener, but blends of them. And so this is looking at a particular beverage, and no longer remember what it is. But it's the classic with sucrose. This is light with one high potency sweetener. This has got multiple high potency sweeteners. And so here is the full sugar beverage in terms of spider plot of sensory properties. And here's the light one, so a single high potency sweetener. Quite different than the sugar sweetener. And then they said, okay, let's use some blend of them. And the blend of 4 gave them this, which is more similar. And we do find blends being used more commonly. Whether it just gives you a better balance or better sweetness, I don't know, but that's certainly the pathway that's used today. It's a black currant, okay, a blend of 4. And you wonder why that happens or what was that due to. Well, aspartame, I think you're aware of course, is a 2-amino acid. And we do have a free amino acid on that, so that is a chemically reactive molecule. And for that reason, it doesn't do well in baking, the Maillard reaction. You put it in cake, you put it in something sweet, you bake that, you stand a real good chance of that amine group on the aspartame reacting with the sugar that you just put in. So the Maillard reaction. And so we'll discuss this later. I'll show you some data from Jean-Paul about the loss of this particular sweetener. Again, other studies, off-flavors that come from a sweetener, cyclamate. We don't use cyclamate. Okay in Canada, it's not okay in the US. I don't know how broadly around the world it's approved, but for one reason or another, it's been disapproved. But other countries still use it. There's off-flavor that came from it for cyclamate degrading in the product, so it was a source of off-flavor. And Jean-Paul studied a paper on aspartame in chewing gum. Okay, we're still not going to get to that one yet. That's coming up. How's that? So high potency sweeteners, simple sugars, they can have a variable effect. How about complex carbohydrates? What happens when we start looking at starches in a food? Or gums, whether it's a guar, or carboxymethyl cellulose, whatever. It's interesting, there is a general effect when a material gives viscosity or a gel that increases the flavor need. So if you put enough in that it makes it thick, you'll have to put more flavor to it. And the effect of this is pretty well illustrated in some work that Deborah Roberts did. And it comes out of Terry Acree's laboratory. I should have looked ahead and see if we're going to deal with this in more detail. Let me just make a quick look. No, we're not. Okay. Then let's go back to it and make a point at this point. Okay. So idea gums, and in this case guar, and carboxymethyl cellulose, and sucrose. So we got 3 materials used individually, and solutions were made up of sucrose, guar, and carboxymethyl cellulose to the same viscosity. So, but I don't know how much sucrose it took to have the same viscosity that guar or CMC. But okay, do that enough sugar. And so this is a plot where Deborah made up 3 different viscosity levels, so 3 different viscosity levels, and this is looking at the volatility of that chemical in that solution. So you make up, this is no sucrose, no carboxymethyl cellulose, no guar. Okay, we have this volatility, this contribution to sensory perception. Then all of these now, a different viscosity. And so what we have changing here, these 2 are pretty much following the same line. Guar and carboxymethyl cellulose, they're following the same line. They were reduced a little bit by being viscous, but not nearly as much as when you added sucrose. So the idea that in the previous slide we talked about you increase viscosity, you decrease perception. Well, it's not that simple. These are all the same viscosity. they did reduce perception, but one acted very differently than the other one. Pinene is a very fat soluble, a very lipophilic molecule. If we look at something that's a little more neutral along those lines, vanillin, that's both water soluble and oil soluble to some level. And so did exactly the same thing, put vanillin in there, and guess what? The system didn't care whether or not it was sucrose or the gums. So it isn't just the idea of viscosity. There's something that happens between these two. And so what basically happens is when you put sucrose into solution, the solution becomes more hydrophobic. You might say sugar. No, sugar is hydrophilic. Sugar is hydrophilic, but it's more hydrophobic than water. And so back here, we've got a pure water system. Here, we're getting a somewhat hydrophobic water-sugar system. And this was much more hydrophobic, much better solvent for the flavor than these other materials. So really good solvent, this sucrose, somewhat non-polar solution. Over here, vanillin doesn't much care whether it's hydrophobic or not. It's soluble in both of them to some extent. So it's actually no effect of adding viscosity. There's actually no effect of changing the polarity on the system. And I like that one because that's, in my opinion, that's basically why perception goes down when you add sugar to systems. Basically, you've got a better solvent, and it doesn't force the flavor out. Its flavor is pretty soluble in the system. And this is viscosity effects depends upon the thickener. Sure. So just what we were looking at. Sucrose has a much greater effect. That really does change your perception a great deal in comparison to carboxymethyl cellulose or guar. If we kind of go through all of our studies, the carboxymethyl cellulose had a little more interaction, a little more effect than guar does. And so it's an interesting one. Is there a texture effect? If something is more viscous, is it perceived differently? You know, if there's no change in volatile release, is it also a perceptual thing? And that's people were spent a good deal of time back this in 1995. And it's really interesting that people hypothesize that if something is more viscous, it doesn't spread in the mouth. There's not as much surface area for the flavor to be released into the mouth, oral cavity, in sense. There's been a lot of nice theories about things get thicker, they just aren't released as much in the mouth, and therefore that's the effect. It's a physical effect. There's a barrier to release in that sense. And that actually stood for some time. And in some cases it still exists, but I'll show you some examples where it doesn't exist. So interactions, often there's no significant interaction between these viscosity effects or gelling effects. I'm going to show you a slide where there is, which is interesting too. You know, why is that? Oftentimes the effect's too general, loss in intensity, but not generally change in character. Flavor concentration. Let's go on to something else. And this is one that I think is kind of interesting. People are leaning a little bit to it this way. Why does something viscous have less flavor? And so there's some question about cognitive effects. Have we learned through laser association that a viscous material is less sweet? So is it real, this sort of effect, or is it something that we've established? And we're tending to lean that direction. That we just judge things less flavorful if they're viscous than if they're a free-flowing liquid. The next slide is kind of what brought that home. Okay, that's 2002. 95, okay, the theory was that this doesn't spread in the mouth, doesn't release. That was the 1995 theory. So this is where Andrew Taylor No, it's a group from Denmark. Group in Denmark, the mass spectrometer of some of these mills, and said, okay, we're going to be monitoring exactly what comes past your olfactory region. Okay. Then we're going to go ahead and take some whey protein of different gel strengths. And they're going to go ahead and put a flavor into that. And then have you put it in your mouth and chew it and swallow it. So what you find is, this is the time of intensity. So this is sensory rating. And so this is a very thick gel. This is a less thick gel. This is a really runny gel. So we've got, let's say, liquids to very strong gels. And each of these, they also were monitoring the true concentration of those was given. And there's really no significant difference. You try and put this together, you are given exactly the same perception, same amount of the role chemicals in each of those cases. And yet, they were perceived differently. That's interesting. And so, when we look at a study like this is a bunch of gels. So they were actually formulated with different hydrocolloids to different degrees of hardness, and this is then the overall flavor, so again, the sensory perception. And as they got harder, they were perceived as being less flavorful. So whether you talk about something viscous or you talk about gels, there is that expectation. And our data is pointing more and more towards it being cognitive rather than a physical chemical property goes on. And so this is basically from that last slide. And at the point they were arguing about, is this breakdown the mouth or is it a cognitive effect? And like I say, leaning more towards what the brain expects out of things. And so there's some exceptions to this last one. There's some outliers. Here's a gelatin as an outlier. Here's a kelp gum, kelp shell outlier. Most of these different, each of these are different material, different concentrations to get these different gel strengths. And some obviously lie outside that boundary. And the general finding was, okay, but basically, what about these exceptions? The two that didn't fit this plot, and that may well have been where there are real chemical reactions occurring between these thickeners. Gelatin, for example, gelatin's a protein. Protein reacts with flavor, and so in some cases there may have been a real chemical effect. We don't really have much information on many polymers, food carbohydrate polymers, been very little studied. Modified starches, we use that all the time in encapsulation. Octanyl succinic acids derivatize starches. They're going to be hydrophobic. They're going to have a hydrophobic nature to them. And so there's the lipofilm, and there's also a long portion. Nobody's ever looked at that in terms of their influence on perception. Gummification contains protein. Let me show you how reactive proteins are. So how is our flavor changed by using gummification? We really look at alginates, carrageenans, well, really lots of potential active reactive sites on these materials. And actually, no one's ever looked at them. No one's ever gone. We looked at starch, looked at simple sugars, but we haven't really gone beyond that. A little bit of gels, but for the most part, these have been ignored. Focus and noir, they tend to be rather boring from a chemical standpoint. There's nothing special, no reactive sites, no special groups on them. We wouldn't expect there to be much of an effect. And so the idea, we've got a lot of potential for binding interactions as well. So physical effects and interactions that we just haven't done. Starches, yeah, they've been looked at really pretty well. And this is some old data. It says alcohols are bound onto starches more quickly, more readily than aldehydes, and they're bound more readily than ketones. So different parts of your flavor will bind different flavor compounds. And I think everybody's familiar with amylose. Amylose is forming, you gelatinize it at retrogrades. It forms an alpha helical structure. Alpha helical structure is a really nice place for a flavor molecule to get inside. And it's actually used to deliver flavor in some cases. Put flavor inside that alpha helix and then put it into a food product. And so amylose much greater effect than amylose. And there's a preference. Some parts of your flavor want to go into that starch more than other parts of your flavor. And that discussion kind of comes here, linear portion. So starches high in amylose will have the greatest effects. Those starches that are lower in amylose probably have less effect upon your flavor system. This one I kind of like too. That's from Andrew Taylor. Again, 1996. There was a period where everybody was interested in flavor interactions. It's kind of like any other basic science, I suppose. Somebody discovers something, everybody jumps on the bandwagon. Now we're going to do this. Well, that's kind of getting boring. It lets somebody else find something else. Oh, let's do this. And so kind of globally, people shift from this interest to that one, to that one, to that one. So this interaction thing really happened to a great extent in the 80s and 90s. And this is now where Andrew Taylor put starch into solution and basically put different flavor molecules into that starch block solution. It's a gelatinous starch. And so here's time 0. All these chemicals were put into the aqueous solution of starch. And then simply monitored the volatility, the freedom of these molecules over time. And within an hour, so here's, what's that? Is that diacetyl? Okay. So what diacetyl? Diacetyl moves away rather quickly. Within 15 minutes, it went from 100% vapor pressure volatility down to about 25, maybe 30%. Different chemicals were bound to different degrees. So you put a flavor, this complex mixture, into a starch, what's going to happen? Some of them are going to be almost unaffected. Other ones are going to be swallowed up by the starch. And so, again, when you make a product, when you flavor a product, you design a flavoring for a product. You will go ahead and add your flavor. You'll come up with something you think is halfway decent, but then you let it sit overnight. And then you look at it tomorrow and see what it thinks, because this has to happen. And so it changes the flavor a great deal. It happens over time. Chemical reactions or simply getting bound up in the alpha helical structure of starch. And some things fit better, some don't. That dodecane, that's not a flavor compound. The rest of them are. There was just an interest in what happens with a real hydrocarbon, a really non-polar material. And so again, how much a flavor reacts and how it reacts depends upon the starch history. So it depends upon the starch itself, alpha amylose amylopectin blend. It depends upon the granules, the structure. Is it gelatinized? Isn't it gelatinized? What kind of cooling process that goes through as well? And so again, starch, very reactive. I think we've said enough about cyclodextrins, so we're going to go ahead and skip these. It's interesting. I visited a flavor company last week, Synergy Flavor. Never heard of them. They're in about a $145 cab ride north of O'Hare. I do remember that. And I was so happy I wasn't paying for it, but I felt guilty turning in like, oh God, I hitchhiked Uber. But anyway, but I asked them what's happening with cyclodextrins, because that was really a hot topic for a while. Oh my gosh, remember that you can flavor molecules move inside cyclodextrins or protected? But everybody, no, we said, no, they're gone by. Their cyclodextrins just weren't finding much use in the food industry, flavor industry anymore. And that was again interesting. Initially, everyone excited, so much for that. So, some of your comments about carbohydrates. Carbohydrates will influence overall flavor intensity and character. Is it physical? Release? Is it chemical binding, or is it human? Is it perceptual? They certainly differ in their effect on flavor. If you change from simple sugar to high potency sweetener to high fructose corn syrup, expect the effect. It's going to influence your flavor. going to change the polarity of the product that you put your flavor into. And so it's definitely going to change. Interactions, I love that one, are complex and unpredictable. And so, for fat, we can say, no, we got fat down. We know it's going to happen. We may not be able to fix it, but we know it's going to happen. When you get to carbohydrates, you don't know what's going to happen. And it really hasn't been studied well enough to have some good predictions. So it's an interesting one. We're going to spend some time with proteins. I'd like to make that uninterrupted, so let's take a 10-minute break now, and then we'll go through the protein part. So let's be back at 5 to 5. And if you haven't downloaded the lecture, you might want to do it this time, because this is where it's different from what I sent you. So you got a new one today. With foods, and it's one that we don't understand particularly well. So there is one other presentation I wanted to spend a little time with tonight, and that's baking. So you should have gotten baking as well. Vaide's kind of preparing, and I think Yara went to help him as well, set up a laboratory for tonight, and that's about applications, how you put flavors into foods, how do you properly flavor foods. And that's a book in itself, but I just wanted to start and say something about baking as one application. And so that's what I'll spend a few minutes in lectures on. That isn't ultimately what we're going to do tonight. We're going to look more generally at flavor interactions. Okay, now I've lost it, but we might actually be successful. Okay, that isn't what I want, but you see it, so it must work, right? Okay, or else I'll be sitting downstairs at night going through this lecture again and saying this is the missed part you missed. Okay, okay, so let's go ahead and take a look at this. So flavor applications, how to design flavoring. Well, when it comes down to it, basically, you're going to deal with a company, you're going to deal with hopefully a scientist. And these are some of the things that you ask, basically. And this is what we talked about when we talked about creation. What are the considerations when you start thinking about a flavoring material? And so natural, artificial, WNF, kosher, halal, clean label, and so on. There's a lot of considerations. Now, I want to see something first. Okay, I just wanted to make sure this was the right lecture. Okay. Because we want to get into baked goods. This is 5. This is number 5.
You just put the slide. The next slide.
Okay. Okay. Like there. Does that look familiar? Flavoring baked goods. Okay. I wasn't sure about the prelude to this. How's that? Okay. It is. Okay, why aren't you seeing it and I am? You'll figure out that I've gone the whole semester without figuring it out. Kind of profound. Could be. Okay. Okay. This is one area that we really don't have any guidance in the literature. We don't have a lot written about flavors. Flavors tend to be very secretive. Companies protect their formulations. They protect how things are done. That's their livelihood. They can't file patents to protect it. They have to have confidentiality. And so we find some books on flavors, but they tend to be oftentimes symposia. They tend to be very different focus. And so we've got a little bit on flavor, but we have really nothing on applications. How should you use the flavor in a food? And that's going to be a chapter on baked goods, a chapter on dairy products, a chapter on each of the products, because they're all different. And so this is just one part of what should be a book dealing with application, how to use a flavor. And so when we really look at an idea of how do we apply flavors, how do we design them, and how do we apply them, we have to take a look at obviously the process and the formulation they're going to go through. So in a very general sense, I think we can say they're cereal-based. Maybe we'll change that to other protein or other things based. But right now, when we think of breads, we tend to think of cereal, beginning of the product. They are baked in an oven, or they could be fried. And so we got quite a variety, but that's what we're going to start with. We're going to start with typically wheat flour, and it's going to go through a thermal process. So our flavor must be compatible with protein that's in flour, wheat flour, from a reactivity standpoint, from an interaction standpoint. It's got to be thermally stable so that it isn't evaporated during the baking process. So right away we got some constraints on how we design that flavor. So in more detail, flour, 9 to 12% protein. Okay, so that brings protein and carbohydrate, but we've talked about interactions, how flavors interact with them. Eggs bring in a different protein, a different reactivity of protein. They bring in some lipids. Shortening or butter is typically put in, depends on the bread you're making, and certainly the fat content. Oh, now we think about how we're going to balance the flavor that comes out of a product that has fat and varying contents of fat. And we are going to put something in for flavoring, whether that's an herb, a spice, what is the active components of that, how do they react. So we've got flavor being formed from the Maillard reaction, from the Browning reaction, whatever. But we also may be adding a separate flavor to give it a spice or herb note. There is a liquid that can be eggs, milk, or water. Okay, water doesn't do much for us, but certainly milk brings in protein, more chemical reactions, different chemical reactions. Leavening, that's going to change our pH. Now my flavor has to be soluble and stable under the pH if it's a chemically leavened product, right? And so that's going to change our environment a great deal and going to change reactivity. So sugar in many products, and of course salt. So again, when we design the flavor, we've got to think about what is our composition and what is our, of course, thermal process. You think about where can you add a flavor? How might you add a flavor to a baked good? Well, in some cases, you're making a dough, so you're adding it to the dough itself. One of my favorite breads are limpa. I grew up in a Swedish family. Okay, what's limpa? It's basically kind of a licorice character, molasses, brown sugar, anise and fennel, that's our licorice character, and caraway. So you put these spices in, these flavorings in, what happens? So mixing in the dough, these spices are put in at the dough stage. We might cheat. Let's put the flavor on when it comes out of the brush. We're going to spray it on the surface with the oil coating, and there's going to be our butter character that everyone might say, that's cheating. But it makes a lot of sense. It doesn't have to go through all the chemical reactions or the thermal processing. Or maybe dusting on the surface. That can also be good. In some cases, our big products are cream filled, or they're filled in one way or the jams, creams, whatever. So again, we've got different ways to apply that flavoring. Different composition, different formulation, different way of applying it in the flavoring material. Historically, of course, the flavoring has come from the ingredients. And so that you added, yes, maybe some spices or herbs, but you didn't really add baked flavor to it. And today that's less so. So we are adding more flavorings. The systems are certainly changing. You may want less sugar. Whole wheat breads can be fairly high in sugar simply to block the bitterness of whole wheat. And so you might be getting less sugar simply for the low calories. So there goes some of our flavor from. They may be high protein. Again, here goes some of our flavor. You might be doing ingredients substitutions. You're going to do gluten free. So now you're not interacting with flavors and interacting with wheat flour. It's interacting with something new, something different. They're making an allergen free desire. Gluten free, high fiber. And again, what are you going to do to the flavor formulation when you start adding these limitations to the process? So your flavoring must survive preparation of the dough, the rising of the dough, fermentation, steam, chemical leavening, chemical treatment of the dough. Sodium metabisulfite is no conditioner in cookies. Thermal processing, like I say, cooling packaging, and so on. So your flavor has to be really pretty robust to survive this whole process. And so what do you find? The flavors are very commonly lipid soluble. They're fat-based flavorings. Why? Less vapor pressure, less volatile losses. Inherently, higher levels of flavor have to be used. It's an oil soluble. Just remember that oil suppresses your flavor perception, flavor release. And so putting a lipid-based flavor is good for the baking process return. However, must migrate from fat droplets into the space. And then be lost. If they're lost, then they actually have to, they're protected in the emulsion or the dough. To be lost, they got to go from there to the dough, migrate out of the dough to here to be lost. So there's a barrier. There's a pretty good barrier that's put in there once we put a fat soluble flavor in the system. And again, oftentimes we use more potent flavoring materials, folded oils, terpeneless oils. They're just more heat stable. And so you design your flavor for meeting those needs. This one of the French students had come over. We used to get a lot of students from INRA and come over, and they'd come over for 5 months and do a project with us. And this is Sophie that came over for this, and she was looking at flavoring cookies. And so what you'll see is her result of flavoring cookies and flavor stability. She did 3 different cookie formulations, regular, low-fat, and meringue cookies. And this is the formulation that basically she had for each of her cookies. So flour, sugar, butter, egg white, of course, in the meringue. That has to be very, very high. Egg yolk, of course, not over there, but some here for emulsification. And of course, meringue cookies are air leavened instead of baking powder. So it's about the same. Moisture content is certainly higher than the meringue cookie versus the other cookies. And so these are, you look at fat content too. Very different flavor, very different products that you would be working with. And so the formulations, of course, it's probably now hard to see a red on the blue background. So these are actually the percent formulations of each of the components you saw. So you should be able to read it, I hope, in your notes instead. And in regular low-fat cookies, different ways that they were made. So white and egg yolks, flavor compounds, blended, cooked it for regular low-fat cookies. You should be familiar, I hope, that they make cookies at home. Okay. Sugar is then put in, blended, soft water, flour, salt, baking powder. Cookies, 15-gram cookies going through the baking process and cooled. So she made cookies, obviously, and added the flavoring back up in the very beginning of the process. So the flavor went through the whole mixing and baking process. For meringue cookies, it was certainly a simpler process where you do the aroma compounds, the egg whites and salt, and make your blender do your egg white whipping and again go through the process. And that was interesting. She used a model flavor system and put in flavor compounds that would vary in volatility: ethyl acetate, ethyl butyrate, ethyl caprolate, ethyl caprolate, 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 and caprate. And so use these different aroma compounds that would fit into the dough to begin with the process. And then looked at their retention. When these compounds were put into ethanol, so it's a water-soluble flavor, conventional baking. Here's an 80%, 20%, so we've got some fat in the system. She also did some microwave baking of the cookies in the ethanol flavor and ethanol flavor emulsion. So baking process, microwave process for the cookies. And this is how much of the flavor was actually retained. And so percent retention. We had starting material 100% in the dough, the cookie dough. Well, 19.3% of acetate. She lost over 80% of the flavor to evaporation of the cookie. And of course, as you go to flavor compounds that are less volatile, you get better retention and obviously. When you put a little bit of oil in that system, you didn't have too much of an effect here because ethyl acetate is limited oil solubility. But as we go to the more lipophilic materials, the percentage retention picked up. If you think about microwave cookies, I never microwaved a cookie. We never would microwave a cookie. You see that there's a little better retention of all these pieces in microwaving the cookie instead of baking. But you lose a good deal of flavor in the process. Having a lipophilic cookie dough is helpful in terms of returning flavors. And this is, I guess, more of a graphic. This is a graphic view of the regular cookies, low fat, and granules. And so again, 10% retention. Regular cookies, 48%. Low fat cookies, 35%. Meringues, only about 8% of the ethyl acetate. And that was true. Basically, regular cookies, we had higher retention than we did in low fat cookies. So there's more fat. More fat to protect the flavor. The flavoring was right into the fat. It held on to it. Meringues had low fat. You see certainly the difference. There's an awful lot of data that's presented in this presentation from the work. When flavors added in the liquid phase, so lost during preparation, lost during baking. So you lose flavor during the preparation. You've got this mixing and whipping in some cases, whipping the butter. And so there's some loss in preparation. And if you think about it, okay, this is the preparation of the dough. This is just before baking. So here you work the flavor into a dough. Here you put it in as an ingredient in the community. So again, when do you add flavor? In the ingredient stages, mixing, or you would try to add it and work it into a dough. And of course, the total loss is listed. You can find there actually, this is percent loss during baking. So okay, that's kind of the opposite of the other one. The other one is flavor retention. This is flavor loss. So it's loss during baking. So 62%. I was kind of looking at it and saying that doesn't necessarily make sense. But, okay. So loss during baking, preparation, loss of baking, total loss. So total loss cost 84% of this compound, 68% of that compound, and so on. When it's added in the dough as you're making it, here it's added to the dough after you've made the dough. So again, difference in when the flavor is added. Is it added as an ingredient, or is it added, like I say, to the finished dough before it goes in the oven? Influence of baking mode, conventional ovens. This is good retention. You got to read this. Is it retention or is it loss? Okay. You know.
On the last slide, the addition of liquid phase, what does that mean? Just like the liquid ingredient?
It was added. The flavor was added to the fat. There was a fat in the formula, so it's added to the fat first. And so again, you look at flavor loss. This is conventional oven, 375 Fahrenheit for 10 minutes. This is 425 degree oven for 7 minutes, and that's microwave. You might think, oh my gosh, microwaving is only 4 minutes and 30 seconds in the microwave. But in fact, our greatest losses occurred in the microwave oven. You tend to lose a good deal of water in the microwave oven, and that water tends to steam distill out the flavor. So baking at 375, much better retention than 425. So lower temperature, longer time, beats high temperature, short time. Influence of flavor carrier, flavor gum acacia powder, flavor ethanol. Okay. So this is looking at encapsulated flavor. So let's take our mixture of esters and encapsulate them by spray drying. If we encapsulate the flavor rather than adding it as a liquid, so we add it as a dry powder, does that offer some protection? And it certainly does. The blue bar is the retention. If we add ethyl acetate as an encapsulated product. So the encapsulated product has more retention than adding the flavor as a liquid. So encapsulation does offer some protection to the flavoring material. This is encapsulating different materials. What's it encapsulated in? There's different carrier materials you can use for spray drying. You put the flavor into a modified starch. So these are 2 modified starches. You add it as modified starch, you add it as gum acacia. And so that's probably the best comparison. Or you add it just as a liquid. So that's a liquid flavor. This is encapsulated in a modified starch. This is encapsulated in gum acacia. So here's our retention again of these products. Ethyl acetate as a liquid. You lose most of your flavoring material. If we look at the modified starch and gum acacia, so again in this case, encapsulating gum acacia with better retention than encapsulating in modified starch for all of our 100 compounds. So these are probably no difference out here between encapsulation methods. So again, how do you add your flavor? When do you add your flavor? What form do you add the flavor? Influences how this product is ultimately flavored.
You know what the CR in the previous graph? The envelope CR and the Roma packet CR?
Down here?
Yeah.
I don't remember. I'd have to go back and read her report. That's why I kind of went over it. I know they're modified starch, CR. I don't have a famous idea what CR is at the moment. Right. So anyway, but they are encapsulated in that material. Chemical 11 products, pH is 6 to 8. That's actually really detrimental to flavor. Flavors such as almond, butterscotch, caraway, cinnamon, ginger, honey, vanilla really hurts them if you put those flavors into a chemical 11 product. Why do you think that is? What's almond flavor? But chemical? Oops. That's aldehyde. Yeah. Do you think that reacts in the oven with the protein? So it's like Vitae, except now we put it in the oven to make it even go faster. So sure, all of these materials, except honey, I don't remember. Phenylethyl acetate, I'm not sure for that. But most of these I know, again, have carbonyl compounds. And so what happens when you put these carbonyl-based flavors into an oven? You're going to react with the protein. And you really jacked up the temperature just to make them go even faster. So, 10 minutes, what we found at room temperature, what do you think that is? We're baking temperatures. Encapsulation, double coating, thermal release. And so one of the things we were interested in, if we spray dry the product, and then we put a fat coating around each droplet.
Sorry, on the previous slide, was there something specific to pH that goes?
This one? Or?
No, the chemical 11. You just say that putting it into the
is detrimental to those flavors, but is there something specific to pH that's detrimental to them?
Bayer grass, right? Doesn't that love an alkaline pH? It loves an alkaline pH. So what have we done? We put it in an alkaline environment, we jacked up the temperature. So are we surprised that these flavors don't do well? No, we're not surprised at all. They shouldn't. So our interest, was can they double coat these materials? And that's hard to do. It's really hard to coat, but what we want to do is we wanted to put a water barrier around each droplet. But that's tough to do on a 30 micron particle, to put a nice coating of fat around every 30 micron particle. But that was certainly one of our goals. If we could slow down the thermal release, if we could protect it from water, our reaction would be much, much slower at the low water activity of that particle. So that would been a solution that we would hope would work. How about savory crackers? What are savory crackers? Flour, water, shortening, they're really simple formulations. Then, of course, you put your spices and herbs into them, whatever. So you get it. But the simplest cracker is just flour, water, shortening. Then they may be fermented to get some kind of leavening to them, sponge, rest of flour, rise again. So the spices that are flavored that go into these types of crackers are usually a spice or a cheese flavor. Spice oils, if you're thinking about a fermentation or leavening, spice oils will inhibit microorganisms. Wouldn't you know? They'll inhibit the yeast. So if you're going to be any chemical leavening of a cracker, it may not be a problem. It depends upon which spice oil that you use. And of course, what happens to cheese? Basically, you lose some of the flavor. It evaporates during the baking process. Very thin layer material. It's not a loaf of bread. Loaf of bread, let's make it a big one. It's a thin cracker with lots of surface area. And so what happens, you lose the flavor of cheese, it evaporates off, and you get browning again taking place. So again, losing flavor from that standpoint. Really the easiest, like I say, I said it's cheating when I looked at that. Spray it on after. Can you do that? Can you put it in oil? Can you add some of the components you want by a spray? Typically, you put flavor into an oil, you spray the oil in the product, but that must be an antioxidant in that oil so that the flavor doesn't deteriorate. Especially good for thin finished goods. Dusted on flavors, coat a cracker with oil, dust on a dry flavoring. So either liquid spray or a dry powder encapsulated spray. Fillings. Again, there's different fillings that you can use, dairy synthetic whipped cream fillings. These don't go through the oven, and so you don't have the same problem with losses or chemical reactions. So there really aren't many problems with the cream fillings. So you go ahead and bake your product, and then you go ahead and make cream half and half, whatever, and then inject it into the center. Little problem, make it distinguish your foam cream from citrus. So if you want to flavor that, citrus doesn't work well. It's not a very good component to be adding with cream. And so use citrus extracts instead of essential oils. Buttercream, so you can have dairy synthetic creams, buttercreams, butter sugar mixture, blend in gelatin, get a marshmallow style texture, butter. Fondant, again, non-fat dry milk, it's butter. So basically, different sweet, buttery fillings. Sweet flavors most appropriate. You do have gelatin as a protein, so you can get some chemical reaction, but again, it's not during the baking process. So the reaction is slow. So you don't tend to have a flavor problem with buttercream either. Or fondants, custard. Traditional starch-based custard mix is boiled, cooled to 60 to 70 degrees. Add a flavor, and then the custard can go inside of some kind of a shell, some kind of a baked good. Flavoring systems, different types of flavoring systems, encapsulated flavors, plated flavors, baker's emulsions, liquids, oils, pastes, all kinds of choices that you can make for flavoring baking products. Here's one mixture, baker's emulsion, so 1 to 20% oil, some xanthan, tragacanth, Sodium benzoate as a preservative, citric acid for a little bit of tartness. So again, they can be used in baking applications to work into a batter, to work into a dough. Glazings, icings, I think that's the last one. Simple mixtures of liquid and sugar, more complex maybe fat stabilized foaming, but simply a glazing, an icing on a cake. Not much happens to it. Can get some interactions between the glaze itself. Again, it's generally a little problem once it's been balanced. So there's fat in it or not, or so on. So you get some loss over long time storage, but it doesn't, like I say, it doesn't go through a baking process. So not many problems. But that was the last one. So I think that's everything I wanted to go through. I will send an example test out to you. I'll try not to ask the same questions I'm going to ask you in the exam.
You could.
Okay, I'll consider it. I'll give some thought. But anyways, so we should see in this same room. I think that works out. So this coming Tuesday, like I say, plan on an hour for it. If you got any questions, by all means, give a holler. Have a good evening.